say much more, I guess, before I start. It's a pleasure to be here. So I will continue talking about entanglement and sort of basic questions in entanglement in a sense. But I want to motivate this in a slightly different way than things we've been talking about this week. So I guess we're all happy about entanglement. We like it very much. And as we just heard very clearly, for us, usually we think about entanglement really as a resource, like in quantum information and quantum computation. But of course, entanglement is also very important in other fields of physics. For example, in many-body physics, it teaches us about phases of matter and how we can discern them. Famously, it's very important for devising numerical algorithms like tensor network methods. And then there are even more fun things like toy models for quantum gravity, where entanglement plays an important role, or the black hole information paradox, and so on. And at least for many-body physics and these latter things, it's very natural to consider entanglement in a setting where we don't have finitely many degrees of freedom, but we actually have infinitely many degrees of freedom, like properly infinitely many degrees of freedom. But our sort of rigorous understanding of entanglement is mostly limited, I think it's fair to say, to settings where we have finitely many degrees of freedoms, and in fact, mostly even finite dimensional Hilbert spaces. So you can ask what happens if we go to these settings where we have really infinitely many degrees of freedom. And this is the topic of this talk, basically. And what we find then is that, it's a small spoiler, you will find different kinds of being infinitely entangled. And importantly, these different kinds of being infinitely entangled can also have consequences for finite-sized systems, for example, in many-body physics. And I will give you an example of that in a second. Okay. So the example that I want to give you has to do with embezzlement of entanglement. So some of you might have seen this before. In the systems with infinitely many degrees of freedom, there's a sort of new entanglement phenomenon. Namely, you can have these embezzling states, sorry. Here, this omega. So an embezzling state is an entangled resource state that is shared between two parties, Alice and Bob, and has the property that Alice and Bob can, for any precision that they want, and for any finite dimensional pure entangled state that they want, they can sort of get out the state from their resource state using just local operations without communication. And importantly, this resource state doesn't really change much. So it's perturbed arbitrarily little. So this is a sort of surprising thing that this is possible, and you can illustrate this with this chocolate trick. Some of you have seen this before, I guess, where you sort of slice up chocolate into multiple pieces, and then you rearrange that, and it seems like you got out a piece for free. And of course, here it's sort of easy to see what's happening. You're sort of stealing very small pieces of the chocolate. But in entanglement, it's more tricky. Okay. Now you might say, okay, this might just be a bizarre mathematical artifact, and maybe it doesn't actually happen in physics, but it actually does happen in models that we use. For example, we have shown that if you have a non-interacting critical fermion chain in the thermodynamic limit, then you always have this feature if you do a bipartition into two infinite halves. It's also common in relativistic quantum field theories. And in fact, in these systems, the effect is even stronger, namely that all pure states in the Hilbert space have this property, and that's why we call them universal embezzlers. Okay. So still you might say, okay, this is just an artifact of going to the thermodynamic limit in a many-body system. But it turns out that you can show that if you have a many-body system, and you have this effect in the thermodynamic limit, and now you look at finite-sized versions of your system, then you get an approximate form of this effect, in the sense that Van Damme and Hayden introduced the phenomenon of embezzlement around 20 years ago. So you can check this feature in the thermodynamic limit, and there you will see there's a very clear indication for that, and then you can deduce this approximate embezzlement property for systems where you don't really know how to, say, compute the spectrum. So it would be hard to decide this otherwise. So this is a bit like a phase transition, where in the thermodynamic limit, it's very clear that you have a phase transition. But of course, a phase transition has effects for finite systems as well, and this is sort of similar. And then you might ask, is there some sort of order parameter for these sort of large-scale entanglement properties? And this is basically what I will talk about. Okay. So we just heard about entanglement and LOCC, so I don't have to say much. So we will have Alice and Bob. and they can do LOCC operations. And we are interested in pure state entanglement today. And the thing that we have to do is we have to sort of generalize the mathematical framework a bit. So what we'll do is that instead of associating local subsystems to tensor factors of a Hilbert space, we will model agents with partial access to a joint bipartite system by von Neumann algebra. So a short recap, what's a von Neumann algebra? It's a strongly closed star algebra, bounded operators on a Hilbert space. You will not have to remember this for the talk. Two things that are important is that it's the notion of a commutant, that's all the bounded operators that commute with all the operators in the algebra, and that of a factor. That just means a factor is an algebra where we don't have a non-trivial element that commutes with all the other elements. Okay? So this is what models a purely quantum system, if you wish. Okay. And once we have such a von Neumann algebra, it determines a set of implementable operations, namely those that have Krauss operators in the algebra. Or if you want to do measurements, POVM elements in this algebra. And then we call these kind of channels M inner operations. Okay? And there's a nice lemma that if you have a channel on the full Hilbert space, the following are equivalent. It's an inner operation. It leaves the commutant invariant, so it doesn't do anything to the other part of the system, if you wish. And also there's a sort of Stein string theorem for that. So you get a unitary dilation with the appropriate unitary. Okay. And these will basically model our local operations in the von Neumann. Now you might ask, okay, why von Neumann algebra? Why have to go there? So first answer is it works in models. It's very useful in models. So for example, if you have a fixed sector in a spin system, say the ground state sector, meaning all excitations on the ground state, then subsystems can quite conveniently be described by von Neumann algebras. Similarly, in conformal field theory, you can do that, and relativistic quantum field theory. Although in the latter, the interpretation is slightly tricky. Okay. Another answer would be from an axiomatic point of view. So let me give you that answer as well. So suppose you have an agent that has partial access to some system, then they have some operations that they can do. And you can make some assumptions about the set of operations that the agent can do on the system. And let's do that. Let's put up a few assumptions. First, the operations are closed under composition. They have also full control over some auxiliary systems that they can import. For every channel, they can also implement a unitary dilation. If they have an invertible operation, that they can also implement the inverse operation. And finally, the set is sort of closed under post-selection. You have to model this in the right way, but you can make sense of that. And then it turns out, and this is so far only published in Lautz van Laak's PhD thesis, which is not published yet, but has been written, that these axioms are equivalent to saying that there exists a von Neumann algebra, and the operations of the agent are the inner operations of this von Neumann algebra. Okay? So this sort of axiomatizes the question, what is a subsystem? It does not importantly axiomatize quantum mechanics, right? It's really just about subsystem. You use standard quantum mechanics to arrive at this result. Okay, so now we have settled that subsystems are described by von Neumann algebras, and this is what we'll do in the rest of the talk. So let's get back to pure state entanglement. So the basic question, of course, is when is one vector in our Hilbert space more entangled than another one? And that, of course, means that we can transform psi to phi via an LOCC protocol, and we always assume that we always allow for arbitrarily small errors. And in finite dimensional systems, the answer to that question has been solved by Nielsen, right? It's a majorization condition. But that theorem only holds in those finite dimensional systems, or at least with finitely many degrees of freedom. Okay. So what we have to do to sort of generalize this is we have to settle two things. Namely, what is a bipartite system? Oops. And what are local operations? I already talked about local operations, so let's go to the bipartite system. So what we'll do now is, here's our full system. There's Alice and Bob, and we sort of already agreed that Alice and Bob have their own von Neumann algebras, and of course they have to be commuting. Otherwise, we cannot think of them as being separated. But we would also like to have a notion that Alice and Bob really share the full system between the two, like this, right? And there are different ways to formalize this. One would be to talk about tomography, like the states on the global system can be uniquely determined by correlation experiments. And if you do that, you can formalize this, and it turns out that this is equivalent to saying that these von Neumann algebras are factors that jointly generate all bounded observables on the Hilbert space. Okay, that's a nice criterion, so let's assume that. Turns out there's a different kind of criterion you could write down to model this thing. It's the following. It's related to uniqueness of purifications. Say you have the property that for all vectors in the Hilbert space that have the same Alice marginal, you can find a unitary on Bob that maps one state to the other. This is what we use all the time in quantum information theory, say Ullmann's theorem. It turns out that this is equivalent to a property that's called Hague duality. This, as far as I know, also only appears in Lautz's PhD thesis so far. Hague duality means that Bob's algebra is really the commutant of Alice's algebra. And often this is just assumed, and some people even call this a technical condition, but we see that this is really a meaningful statement. And now the bad thing is that one does not imply the other. So neither of one in general implies the other, but if we assume that MA and MB are factors, then Hague duality implies tomography, but not the other way around. In fact, this failure that tomography implies Hague duality is related to a whole field of mathematics called subvector theory. I will not get into that. What we will do is just simply assume both of them. So for us, the bipartite system will be a pair of commuting factors on a Hilbert space that are commutants of each other. Okay, so this is how we model bipartite systems in the Riemann. And then we can actually prove Nielsen's theorem. So we have two vectors with certain marginals, then we can show that you can go from one to the other via LOCC precisely when one marginal majorizes the other. And here majorization is defined in terms of mixtures of unitaries, because we don't in general have a notion of a spectrum. To define majorization, we have to use the mixture of unitaries condition. I should also note that for so-called semi-finite von Neumann algebras, this result was proven before by Jason Cran et al., and we generalized this to more general cases. Okay, so what's the proof idea? I will not give you the proof. What's the proof idea? It's very simple. You go through the proof in Nielsen and Schwang of the finite dimensional Nielsen's theorem, and then you find objects like square root of rho and inverse of square root of sigma, and you replace such things with corresponding objects in what's called Tomita-Takesaki modular theory, and then you find that the same proof works. Okay, so you just have to identify the right object, and you see that the proof works, basically, up to some fine print. Okay. So we have Nielsen theorem, but what does it tell us? And this will be the rest of the talk. We will see that algebraic properties of these algebras are in close correspondence to entanglement properties, operation entanglement properties. And that's what I want to explain in the rest of the talk. And to do that, I have to tell you about the classification of factors. So these factors can be classified into three different types, which further differentiate into subtypes. For example, we have type 1n, where n is some natural number, and those are just the bound operators on an n-dimensional Hilbert space. Of course, n can be infinite. Then you have type 2, which is subtypes type 2, 1, type 2 infinity, and then type 3 has a continuum of different types, enumerated by some number between 0 and 1. And the semi-finite algebras that I talked briefly about before are type 2 and 1. And type 3 is somehow more difficult often. So the ordinary quantum mechanics plays in type 1. Okay, so what we want to see is that these subtypes and subtypes are in one-to-one correspondence between operation entanglement properties. So in other words, the classification of factors is a classification of operation entanglement properties. Okay. So how do we do that? We say that a state contains infinite one-shot entanglement. If for any finite dimensional entanglement state that you wish for, you can distill it from the state, okay, by some LOCC protocol. And then you can show that two things are equivalent, namely the factors have type 2 or 3, and some / all pure states contain infinite one-shot entanglement. So that means that in this type 2 and type 3, there are no unentangled states because all states are infinitely entangled already, one-shot, in terms of one-shot entanglement. Okay, so this discerns type 1 from the others in squared. This was basically known before, we just generalized it slightly. But how do you discern between type 2 and type 3 and the subtypes? So it turns out that in type 3 factors, this majorization completely trivializes. And then using Nielsen's theorem, it follows that in these type 3 cases, all pure states are LOCC equivalent. That's a bit weird. So you have infinitely many different states, which are all infinitely entangled, but they're all equivalent under LOCC. Particularly, this means that in type 3, no matter what the subtype is, if you look at LOCC operations, they're all embezzling, if you wish. It's a bit weird. And particularly, it means that entanglement monotones for pure states don't really make sense because they're all the same, right? Okay. So we now have this rough distinction between type 1, type 2, and type 3 in terms of one-shot entanglement. You have finite one-shot entanglement in type 1, infinite in the other, and type 3 all states are equivalent. Then we can use maximally entangled states and whether they exist to discern a bit further. So it turns out that in type 1 infinity and type 2 infinity, there are no maximally entangled states. In the remaining cases, there are. So we get this finer subdivision. So now we can distinguish type 1 and type 2 and their subtypes, but we cannot yet distinguish the type 3 subtypes. It turns out you can do that as well, and that you can do via a quantified version of embezzlement. So you can introduce a quantifier that tells you how well all states in your Hilbert space can embezzle entanglement. This kappa max, we introduced this last year. And it turns out that it takes the maximum value for type 1 and type 2, but for type 3, you get this funny function of lambda. People who are familiar with phenomenal algebras might recognize this function. The important point here being that this function is an invertible function of lambda. So that means you can read off lambda from the quality of embezzlement, at least in principle. Okay? So you have different kinds of embezzlement qualities for these different subtypes in type 3. Okay, so we see that really this type classification and subtype classification of factors is really in one-to-one corresponds with entanglement properties of pure state entanglement. And that's basically the main result. One small thing, I said that in type 3, entanglement monotones don't make sense. So what about type 2? Well, in type 2, it turns out you can generalize the notion of a spectrum, and then you can generalize things like Schmidt spectrum, Schmidt rank, which tells you about stochastic LOCC transitions. You can define majorization based on the spectrum. You can define pure state entanglement monotones just like usually by applying functions to the spectrum by entropies. And yeah, check this out if you're interested in. The paper also contains a self-contained review of majorization theory, both for commutative and non-commutative measure spaces. So well, commutative measure spaces and phenomenal algebras. So it might be interesting for some. Okay, so this is almost it, but before I summarize, I would like to sort of give a brief outlook for what you can use all of this for. So I started with this motivation of talking about many-body physics, maybe quantum fields, and so on. And one nice feature when you go to these sort of settings is, for example, you imagine a lattice of spins, and it's partitioned into infinite subsets. And now you act with the quantum channel on any finite number of the spins, or you even change the partition that you have by a finite number of spins. Then it turns out that these properties, like the fact, the types, and whether Hard duality holds or not, these are all preserved under all such kind of perturbations on finitely many degrees of freedoms. So that means that explains why one can think of this really as large-scale entanglement. You cannot change it by acting on finite subsystems. And this is, of course, particularly interesting in many-body systems. And one nice observation, for example, is the following. So many of you will know the classification of gap phases in 2 dimensions in terms of topological order. So there, let me just briefly recall that 2 phases are, or say, two systems are said to be in the same phase if you can connect the Hamiltonians by a path in the space of local Hamiltonians where the spectral gap is open and lower bounded by a constant throughout this whole path. And famously, there's one sort of trivial phase which allows for product ground states. In our case, this means finite entanglement or type 1. But then there are also other phases which are called topologically ordered phases. An example is the Torrey code. Say it's in this phase there. It turns out that one has type 2. And this was shown, and some other models based on like topologically ordered models, quantum doubles of abelian groups, also known to have these type 2 things if you look at cone subsystems, infinite cones of your 2D plane. Okay, so then you might think, okay, maybe somehow there's a connection between these sort of large-scale entanglement properties and long-range entanglement properties that are classified by topological order. It turns out that this is not so clear. So these two are sort of independent, because what we showed is that actually every phase of matter, for example, contains universal embezzlers. So in every phase of matter, you can find many body systems where all finite energy excitation of the ground states have this embezzling property. So somehow, and then the basic reason for that is that all types already appear in the trivial phase, and then you can just stack 2 models, one with the trivial and one ordered phase, and you remain in the same topologically ordered phase, but you can just use the one trivial system to sort of do whatever you want. So what's really interesting is a sort of minimal large-scale entanglement in one phase. And there are certainly phases where you need type 2, for example, like the Torrey code phase. This was shown by Ogata and Neumann. But the general picture is quite unclear. In particular, there's a nice problem, or open question maybe, whether there could be what I'd like to call an embezzling phase of matter, where all systems in the phase are universal embezzlers. And that, I think, is a nice open problem. We wrote an article reviewing these sort of problems and also stating a range of open problems in this field where we try to apply these results to many body physics. So if you're interested in, please have a look. And with that, let me summarize. So what we've seen is that bipartite quantum systems are, or can be modeled, should be modeled by commuting factors, that single-shot properties of all pure states in the system are in one-to-one relation to the types of the factors. You get infinite one-shot entanglement for all states precisely if you have type 2 and type 3. And for individual states, well, you can always map from one to the other in type 3. And in type 1 and 2, you just use the usual majorization criteria that you have to slightly adapt to the type 2 case. So thanks a lot.
Great. So, yeah, there's already the first question. Henrik, can you maybe grab it?
Thanks for a nice talk. Oops. Yeah, okay. Thanks for a nice talk. So you said in type 3, all entangled states are basically equivalent by LCC?
States, yes.
Does that mean that things like self-testing and robustness of non-local games just break down?
I don't know. I don't think so, but there's a sort of complicated reason why I don't think so. There's an mathematical argument you can make that in these cases, so for these sort of correlation game kind of questions, there's at least an intuition that you can make that the type 3 property is not important, that you can sort of reduce this to a type 2 setting, but we haven't really worked this out.
And then the equivalence would go away somehow.
Yeah. So it's not so clear. Of course, I mean, they for example, all states maximally violate CHSH and so on, right? So that you know. yeah, but I can't really tell. I don't know much about non-local games, so I don't want to speculate too much.
Okay, we have one more question here.
Yes, thank you very much. You said that in the type 2-1 case there was a maximally entangled state.
Yes.
I have difficulty imagining that. Could you, for instance, in the product of 2x2 algebras with the trace?
Yes.
What would that be?
It's the traceless state. So it's the purification of the trace.
Minimally entangled, isn't it?
Sorry?
That seems to be minimally entangled.
No, it's maximally entangled. It is, yeah.
Also?
You take infinitely many copies of Bell states, then you get the maximum entangled state in the type 2-1 case. Yeah.
Of trace states?
Yeah.
Okay.
Okay, I think we should thank our speaker again. Many thanks. And then proceed.